This is a walkthrough of Problem 3 on Exam 1 of Module 8 in the book Problem Solving Guide for Electromagnetism and Optics. Problem 3, two parallel wires shown in cross-section in the figure. Right here, the wires are perpendicular to the plane of the page, go a long way into the page and a long way out of the page. The top wire is 40 centimeters above the bottom wire. The top wire carries a current of 3 amps directly out of the page. The bottom wire carries a current of 5 amps directly out of the page. Part A, where is the magnetic field 0? State your answer unambiguously. To figure out where the field's 0, we start by trying to figure out where the field can possibly be 0. For the field to be 0, the field from the bottom wire and the field from the top wire have to be equal in magnitude and opposite in direction. Let's use the right-hand rule and draw the magnetic field around these two wires. There we go. B field, our thumb curls around the wire. Put your thumb in the direction of the wire, which is directly out of the page, and it curls counterclockwise in both cases. So above the wire, the top wire is producing a field to the left. Above the top wire, the bottom wire is producing a field to the left. There's no way they're going to cancel. They're in the same direction. Below the wires, the bottom wire is producing a field to the right. And below the wires, the top wire is producing a field to the right. They're in the same direction. There's no way they can cancel. Between the wires, the bottom wire is producing a magnetic field to the left. The top wire is producing a magnetic field to the right. They're going to cancel in here somewhere, and it's going to be closer to the wire that's carrying the 3 amp current because that current is less than 5 amps. So it needs to be a little bit closer. Now we can do the math. Let's define the distance from the bottom wire up from the bottom wire as x. There's our x. The whole distance is 40 centimeters. This is where the magnetic field 0, a distance x above the bottom wire. B from a long wire in both directions, double infinite. That's what this 2 is for. Mu naught I over 4 pi a. We can set the field from the top wire and the field to the bottom wire equal to the same magnitude. And we can plug in the numbers. The top wire has 3 amps of current. It is 40 centimeters minus x away from the point where we're calculating the field. The bottom wire has a current of 5 amps and it is x away from the point where we're calculating the field. Lots of canceling goes on here. And we end up with just 3x equals 5 times 40 minus x. We can distribute the 5 in there and add 5x to both sides to get 8x, and then divide by 8. X is 200 centimeters over 8, which is 25 centimeters. So the answer is the magnetic field is 0, 25 centimeters directly above the bottom wire. That's part A. Part B asks for the magnetic field 30 centimeters to the right of the top wire. We're going to need a bigger figure. Let's do that. We want to know the field right here. That's 30 centimeters. That's 40 centimeters. A nice 3, 4, 5 triangle is formed right here. To start, we have to get the directions, and this is non-trivial. We're going to use the right-hand rule. We want to know the direction of the magnetic field at this point from this wire, and the direction of the magnetic field at this point from that wire. We're going to curl our fingers around, and we know that if we put the distances in, because they're circles, the B field circles around the wire, the magnetic field vector is going to be perpendicular to those distances. So let's put the distances in. There they are. So the magnetic field at this point from this wire is straight up. the magnetic field at this point from this wire is right there, perpendicular to the distance. Right there. Let's put them in. There's B from the top wire. There's B from the bottom wire. Invest some time getting this direction right, because you're going to do a bunch of algebra to add these two vectors, and if they're in the wrong direction, you got no chance. Stick your thumb out of the page for the bottom wire and curl your fingers around. They're going to point directly over here. Stick your thumb out of the page for the top wire, curl your fingers around. They're going to point directly upwards at this point. Now we can calculate the magnitude of these vectors with the equation. The magnetic field produced by the top wire, mu naught I over 4 pi a times 2, the distance is 30 centimeters, the current is 3 amps, and we get 2 microtesla. This vector is 2 microtesla long, the magnetic field from the top wire. Now the bottom wire. Mu naught 5 amps, and it's half a meter away. That's 50 centimeters, 3, 4, 5 triangle, Pythagorean theorem, and that's also 2 microtesla. So these vectors have the same length. This one's farther away, but it has a bigger current. To add the magnetic field vectors, we need to split this vector into horizontal and vertical components. And to get that, we need the angle, and we can use a number of things. This angle is the same as that angle. Arctangent of 30 centimeters divided by 40 centimeters. That gives us this angle, 36.87 degrees. You can get it any number of ways. So now we get the horizontal and vertical components. The x component is minus 1.6 Tesla. That's 2. That's minus 1.6. And now we need the vertical component. We use the sine of 36.87. That's 1.2 Tesla. So it's up 1.2. And now we can get the magnetic field vector components. B sub x is minus 1.6. That's just from the bottom one. Minus 1.6. And B sub y is 2 plus 1.2, which is 3.2. The magnitude of the magnetic field at this point is thus the square root of B sub x squared plus B sub y squared, which is 3.56 microtesla. Somewhere like that. Now we need to get the direction. I use a different angle, beta, because we use theta for the angle between the bottom and the horizontal. Doesn't matter what we call it, it's 63.4 degrees. So there's the answer. The magnetic field is 3.56 microtesla, 63.4 degrees above the negative x-axis. And there it is. These two, B top and B bottom, are both 2, so this vector is right between them at 63.4 degrees above the negative x-axis. That's problem 3.